Welcome to the session on the unified boot time measurement. I think we are on time to start the session, so I will start the session, right? So this session is basically presented by myself, Vishnu Pratap Singh, right? I'm from Texas Instrument, India. My colleague Soumya Tripathy is also the co-author of this proposal, right? And he's currently not available here, so I'll be presenting the whole session over here. Right, so there is brief introduction about myself and the Soumya. So I have been nearly like 2 decades of industry experience on the Linux-based product development. Everywhere, no different verticals I have been working, right? And Soumya is basically with TI for the last 3 years. His expertise on the bootloader, flash drivers, display controllers, etc. on the SATA MPU devices, right? About TI, so as you know, right, you might have seen some of our previous sessions where we talk about upstream first mentality, where basically our culture is to give back to community. We don't want to have everything behind the walls which we develop, right? So that's where we want to give everything, whatever we develop should go to the community so that everyone can benefit, right? We are part of different Linux Foundation projects like kernel CI, CIP, LF Energy, Yocto, all the different. Okay, let's talk about the agenda for this session. So first thing is basically the problem statement, why we want to solve the solution. What was the issue, right? So that's what we want to discuss over here, right? Then what is the existing boot time measurement approaches we have, what normally most of us use when you do the boot time optimization, right? And then our proposed solution, how basically the unified boot log time based, basically we can measure the boot time. This is basically to solve, right, a problem where when you measure the boot time, you'll not get the unified view of this complete system, what actually exactly happened at each stage, right? And I will talk more about that in the problem statement. So this is the approach. We are not telling this is the kind of final or complete solution, right? It's the approach, how we can solve this problem. That's where we will be needing more help from the community to solve these issues, right? Then what is basically we have done this on the AM62X and the Beagle Play, right? This framework we have experimented and we have the complete result of that. I will show you how the result looks like, what things we have done over there, right? And what is the current status and what's the future plan? That's what we'll discuss more. Okay, let's start with the problem statement. So first thing is that, as I said, there is no unified boot time view for your system, right? When you start your system, your SPL bootloaders, they will have their own timestamping method, which is not basically in line with what kernel timestamps you see, right? And at the same time, when you have the different subsystems like MCUs or DSPs or anything, right, they will have their own timestamp of the boot logs, whatever they have, boot stages, whatever they are, right? So there is no unified view of this complete system from power on till it goes to your file system is running, what exactly happened at each stage, right? So you can't view from end to end. The timeline is very difficult to view, right? Unless you go with the existing method like hardware-based, GPIO toggling and all, right? The second thing, as I said, it's a heterogeneous system complexity, right? Where you have each core running on the different operating system, like Linux is running, then you have the QNX running, some RTOS like Jaifa, free RTOS is running, right? And each component, when you talk about, let's say, MCU or the other core, they will have their own software modules, drivers, etc., right? And they have very significantly size, the complexity, interdependencies, and the resource requirements, whatever they have, right? Also, the inter-component dependencies creates a complex boot structure, right? Which basically have the potential delays and the bottlenecks. Also, when you're trying to optimize the boot time, it's very hard to get the complete picture and debug because of this inter-component dependencies, right? Also, it is the scalability issues, right? When you add a new feature or the system configuration, right? So it basically increases the complexity of this, right? So another thing, why this boot time is important, right? Why we want to do this and what is the KPIs we use, right? So as you all know, boot time is basically the impact for the first impression for any user who's using the system, right? So that's very important to see how the complete system, responsiveness. And also, it requires the KPI-driven optimizations. When you want to optimize a specific use case, you need to know, right, what specific use case I'm going to do and what is the KPI for that. For example, some of the cases like we need the early display, we need the early chime, we need the early CAN or early Ethernet, all the different use cases. And these use cases can run on the different subsystems. It may not be on your U-boot or kernel, it may be on your MCUs or DSPs. So how will solve those things, right? That's another problem over here, right? The product reliability, that's anyway common to know, right? If your boot time is too much, right, then it indicates there is some problem in your system, right? And there is some issue with the system, right? So how do we measure the boot time? What is the first step of measuring or optimizing the boot time? When you want to optimize a boot time, so first key step is that you should have the accurate and consistent boot time. If you don't have, if you change each boot, then it will be very hard to optimize the boot time. So whatever the approach here we are talking, that's basically to have this accurate and consistent boot time for using this framework. Let's take a look of a complex heterogeneous SOC where we have the standard boot, how it looks like. This is for the AM62X EVM and the Beagle Play, where you see from the PMIC, you'll have the power on reset, and then it goes to your secure core, where you have the security firmware running, and the boot master, which is the basically boot master for the complete system. It's master for complete system. It does the device firmware management, your power management on extra, right? And this core, basically the boot master core, it starts the main core, A core, where your SPL and the U-boot runs and your Linux kernel and RTOS runs, right? And from the A core, main core, U-boot, you basically start the MCU cores as well, right? So you see here, it's basically there are one boot master, and then it basically start multiple cores as well in this here, right? So in such kind of system, this is just for reference, right? But we have the multiple other subsystem where it is more than that. This is the single master boot, right? But we have the cascaded boot where let's say your MCU start the other MCU, then that start other subsystem, right? So that case is also there. And it's very difficult in such cases how to get the complete view of the boot time. So here, as I said, so let's take this example of where your U-boot, you need the early audio or early audio plus connectivity. And similarly, from the MCU specific, we want to know early audio and display use cases. So these are some use cases. And the issue over here, what you see, the rapid increase of the SOCs, whatever we are building, variants of that coming up. So each SOC, when it's coming, right, the variant is coming. So each time you have to validate the boot time. What is the boot time of that? And we have to basically repeatedly measure those things. And it's significant testing overhead for us, actually. Right? And as I said, the different use cases, what you see here, so for each use case, we need to have the different measurement schema, right? Because when you're measuring the MCU application over here, where the early audio and display, so you need to have a different mechanism to measure that and see the boot time, right? And when you're going for, let's say, the U-boot based audio plus display or early Ethernet, right? In that case, the schema will change for that, right? So this basically increase and manual effort, testing effort over there, and it's a resource-intensive effort, right? So this is, again, one problem for us. And the other problem we have is the release-to-release consistency, right? Let's say you are on the 6.12 kernel today, and then you are going to 6.17, right? So what happened there, right? There, the release time, after this 6.12, 6.70, there is change in the complete kernel, right? Now, you will see, okay, boot time is increased. Okay, where it is increased, why it is increased, where it is increased. It's very hard. Then you have to go try to pinpoint where it is actually happened, then go and bisect that issue, right? But with this approach, whatever you're trying to solve here, you can run every day whenever you want. You can integrate to your build forms, right? Automatically, you can get the boot time results. So any change happens in that, you should be able to see that. And immediately you can bisect and solve that problem, right? And also the component level analysis, right? So each component, what exactly happened in the, let's say, MCU or DSP, what exactly happening in the each stage in that, right? That also you'll be able to see completely and bisect and solve those issues over there. So main issue here is what we talk is the lack of standardization. We don't have any standardized process for measuring the boot time, right? And that is what makes difficult for the complete this kind of system, heterogeneous system, or this single master boot system. There is no standardization. We have seen something on the U-boot, we see something on the kernel, we see some proprietary on the MCUs, DSPs, all such things, but there is no standard, right? How we are going to measure those things, that is the biggest problem and biggest reason why we are facing all such issues when we do, right? Okay, let's see how we measure the boot time today. I have mentioned few of the things over here, what we commonly use, right? So the first thing is basically the hardware-based measurement methods. So that's where we use, let's say, GPIO toggling and logic analyzer, where at a specific boot stage point, you toggle the GPIO, then that GPIO toggling, you check on the logic analyzer, and so on. You can see the complete boot stage with that, right? So that's one method, which is commonly we use for the accurate measurement. And that method is trace tools like Lauterbach or DS5 that also we can use for the accurate measurement of the boot time, right? And also we can use the external system monitors. Some of the cases we use like power analyzer, CAN receiver, or USB or serial sniffers, right? So these are also used variety. The only problem here with the USB hardware-based measurement method is that you need to have this hardware setup at your desk to measure, right? And you have to modify your code. Let's take example of GPIO toggling, right? So you have to modify your code to add the GPIO toggling at specific points in your either in bootloader or kernel or your MCU code, and then you connect and then right? So these are the issue with the hardware thing. It gives you precise and accurate, but you cannot do it every day, or every engineer cannot do it. Right? They need a specific setup, right? Then we have the software-based measurement method, right? Where we basically use the print logs, then we use some timers, counters, and then we use the trace mechanism. Again, we use the software-based method, but again, the holistic view of the system boot time, we don't get it. At the component level, only we get the boot time. Like at the Linux, we can see that init calls, how it is there, what's happening at each stage. But again, if you want to see the holistic view and the precise and accurate timing, that's something which we miss here. Okay, now I'll just go to whatever is our proposed solution or approach, right? So this is basically, as I said, there is no standardization, right? So what our proposal or approach is there, that we standardize the boot time records across cores, not only at U-boot or kernel, but everywhere else. Whatever the MCUs or subsystems you're using, it should be standardized. Everywhere we should have the same record, right? So this is inspired from the U-boot stage, boot stage recording, right? Means we have a U-boot boot stage, so it is inspired from that. We propose to modify this particular framework and standardize the boot record logging. So this is what is the very initial version, what we are talking about, what it should contain, right? It should have your component ID. That is what you see, the first one, boot record ID. So you have MCUs, DSP, A core, R5, all those cores. So each component will have the component ID to identify this particular subsystem boot record is for this ID. Right? Then you have how many boot record counts, how many records that subsystem has, that information will be there, and then what time that component started, right? So that is the time. And then you'll have different boot stages of that component records mentioned with the profile name, what is the boot stage name, then what is the time that boot marker started. However, we can debate more on this. We want to simplify more and more efficient in terms of memory usage as well. Right now, you see, it's like we are adding the name for the boot stage. We can also add something like the ID for even each boot stage in that. But only problem will come when you're parsing to generate the final report, right? So anyway, we'll talk more on that, right? As I said, so this is the standard boot stage record data which we want to standardize, and it should be basically no, each component level boot, they should use they can use this one for logging their times boot time events, right? And similarly, your A core like U-boot, and no, they can also use the same thing for recording the boot stages. The second part of our proposal right now is that we have recorded all this on the different components, right? Now, how we basically gather at one place, how we basically share it, how we get it, read those records and give you the final input, right? That's where we say unified memory allocation, right? Allocate a memory region which is accessible to all the cores in the system, right? Each core will write, each component will write to this shared memory area these boot records, right? Which will be later processed by the parser utility from the user space to have a unified boot time view, right? This is, again, we are still in the early stage. We are trying to understand, okay, what other way we can do. There is methods. We can use the IPC methods as well to basically each component can have the records within themselves, and using IPC methods, we can retrieve those records as well. So with that, we can avoid basically the memory allocation at all. So that is the another method. That's something we have still to explore those options. Right, as I said, this is the area where each component will be storing the boot records. Let's talk about how our system view looks like, right? I know we have to refine this more, and we need your help on refining these things, right? So when you power on, you see, I'm talking here a simple example where it's a core, your master core based boot only, where your A core will be having your SPL, U-boot, kernel, and U-boot will be starting your MCU subsystem as well. So this is the one view which I'm showing. So basically at SPL U-boot level, as I said, we already had the boot stage feature framework in the U-boot and SPL. So if you enable that feature, right, and then you enable the reporting, and the third point here is stashing. So stashing is where you have to tell what memory area you want to write these records, right? So that is something in the U-boot parameters configuration. You can specify this is the area where I'm going to write my U-boot and SPL boot records, right? So here the U-boot use the architecture agnostic timer get boot US for getting the timestamps for different boot records, right? You see here I have given a sample what kind of time source or counter source we can use on different architectures. However, there are issues with some of architecture, whatever the timer source I have given, right? But this is where we also need to discuss and find out, okay, what sources we can use which can be for these boot records. For example, ARM64, we are currently using the CNTVCT EL0. I think this is what Eric from Red Hat also earlier, I think few years back, they have proposed and using the boot time analysis report in that way. x86, TSC, yeah, I know. It's problematic. We cannot use directly the TSC, but we have to see what else we can use for this, right? Similarly, for MIPS, we can use CP0, and RISC-V, we can have M-time registers, and the MCU or DSP, whatever you have, M4 or R5, you can have your own counters to use this. Right, once you have this timestamp, right, so you have the boot records, you will basically say, okay, these are the boot events I want to record, right? And those events basically you write to your shared memory area, which I explained earlier, right? Once that is there, so U-boot will start your MCU other subsystems. I'm just taking one example of one MCU, right? So MCU will have basically, it will use the same boot structure, whatever we want to standardize. In the current solution, whatever we develop, it is still using the old U-boot structure. Okay. So, and it will use the timestamp. As I said, it's MCU specific timestamp. So it will read that from the timer source, whatever we have, and then it will record all these boot events and then write to the shared memory over here, right? And at the same time, your U-boot will also start the Linux kernel, right? So here, again, we pass the device, the reserved area, the shared memory area using device tree or the boot arcs. Currently, we are doing using the device tree. You pass the size and area using the boot arcs to the kernel. So kernel will basically reserve that area so that no other subsystem can use that area within the kernel, right? And we also propose this config boot time tracker. So this basically what it does, it's again create the architecture agnostic APIs for giving you the timestamp source, right? So again, this we have done for ARM64 using the CNT VCT EL0 register. And once you have, I think the last, Denver, I think Tim has presented adding these two or three locks in the kernel. So similar approach we are taking here as well. So we add two locks, start of the kernel and when the kernel start first user space process, right? So I will get more in detail the next slide, what exactly I have done over there, right? And then once these are there, so these two locks are used by the user space utility, right? Which basically what it does, first it will get the boot record data from the DDR using the devmem interface, and also it will get the kernel timestamp from the dmessage logs, and it fetches all the MCUs, all subsystems, boot logs from the your shared memory area. It calculates the time offset, because here's one more thing is very example. Very important is the time synchronization, because each one is having its own time way of recording these timestamps, right? So time synchronization is very important, right? It has to have the whatever the offset is there from the master core to your other cores. We have to merge those timestamps, right? It should be on the same timeline. So this utility does that as well, right? And once that is there, it will basically sort and merge the complete boot records, and then it generates the final boot report, which you can view on the command line as well as the graphical output in the HTML format. We have a lot of work to do here on the time synchronization part. As I said, it is the single master based boot approach we have taken. When we have the cascaded boot, that's where this time synchronization is more important. I will talk a little more on when our future plans, what we are going to do over there. Okay, so let's talk about how the boot time records propagate from U-boot to kernel, right? So first thing is basically boot record creation in the U-boot, right, where SPL logs early boot events and passes them to U-boot. So here one important thing, SPL logs in the temporary buffer. It is not written to the DDR or anywhere. So once SPL handoff to the U-boot, just before that, it relocate those buffer so that U-boot can access it. Okay. Actual writing to the memory is done by U-boot just before it hand off to the kernel, right? So as I said, this will record all the key milestones. The U-boot will, like you have DRAM in it, MMC in it, whatever. It has a certain specific boot timestamp, boot record IDs already the part of the U-boot. So you can use those. You can add that wherever you want. And then basically these records will be stored in the memory buffer, whatever reserved region, right? So as I said, this boot record location size is exported via the boot aux or device tree, right? Here is some snapshot, right? So as I said, it used the timer get boot US. It's architecture agnostic API. So you can hook whatever platform architecture you are working. You can implement your own methods over there, right? So that you get the exact time. So one important thing here is that whatever the time source you're using in U-boot and SPL, it should be same in the kernel as well. That is very important to get the unified boot time view, right? And if you want to add a marker, right, means a specific boot event in your code, right, you can always use the boot stage mark name, which start with, you will give the boot stage ID. What is the stage ID? As I mentioned, U-boot already has roughly around 250 boot stage ID mentioned there. And the next one is basically you can give a string, which basically when you print those boot records, you can see those in the U-boot. Second stage, as I said, parsing to the kernel. So here we use the boot args for parsing or device tree, right? So you can see here, so yeah, one important thing I missed here is when it write to the shared memory. So you see just before the handoff, it has, I have added this patch, it was not there. So that's RFC push where we have to stash just before handing off to the kernel. So that's there in the announce and cleanup function. You see I have added the boot stage stash default. That is where it writes to the shared memory. We also have to see if there is, whatever we have observed that there is not much impact or delay caused by recording, writing to the DTR area over here. And see, for passing to the kernel, right, in the device tree, you can have the your boot stage DDR node in the reserve mem, right, where you can specify what address that records will start and what is the size of that, which will be later used by the boot parser utility. Going ahead, now we come to the important part is how the non-Linux component uses boot records, right? This is very important because this is what it makes. It's not only specific to Linux. When we say standardizing boot records, means we should have a framework where any subsystem, MCU, M4, K70, whatever you have, right, they should be able to use it. So this is what we have developed this one. You can use this particular framework to any of your subcomponents, right? So what exactly it does, it provides, it is basically give you the initialization of the boot stage record itself, where you pass what is the memory address, shared memory address where you want to store that, okay, how many records are there, all those informations are there. It also provides you your component specific API for having the timestamp source, right? So if you see here, right, boot record get timestamp, so that is what it gives the timestamp, and then at specific profile points where you want to profile your boot time measurement, you add this API, basically boot record log profile with the name, what is the name, right? And then this framework takes care of adding those, the component ID, adding the start time, end time, all such things. This one fully takes care. So this is the important thing on this proposal, what we have done here. Okay, now we are coming to, as I said, we have done this on AM62X and the Beagle Play, right? So how basically we measure and generate the final boot time report here. So preparation, as I said, basically we have to enable the boot stage logging feature in SPL, U-boot, and the kernel boot track marker. And also we have to integrate the previously discussed framework for the MCUs or subsystem to your particular core component, whatever you are using, whatever MCU or DSP are using, you have to integrate their build system and add the profile points over there and load the image to the MCU or DSP, right? I think most of the things I have already explained, basically how the timestamps is done by the SPL and U-boot, and kernel logs for start and end boot time, and MCU logs their boot timestamps to shared memory. So here is some example of how it is there on the Linux side, which I was talking earlier, right? So we had this, okay, boot counter now. So this is again, ARM specific, whatever ARM64 is specific. We have added this primitive file where you can have the counter for getting the timestamp API. So you can develop similar for your x86, MIPS, all other different architecture on the Linux, right? And then As I said, this is the boot stage ID, kernel start and end. You might see why it is starting with 300 or 301, right? So as I said, U-boot already has used more than 250 records. So I have just added a buffer so that no, in future, if you're adding more over there, it should not cross the overlap with the Linux. However, going ahead, when we refine this framework more, we can basically get rid of this completely. We don't need to have, because it gives you a restriction that, okay, you can use only those IDs. But if I want to add my custom profiling I want to do, right, I want to add on different, say, it should not be there. So that's where we are thinking not to go with the IDs in future. Instead of that, just have a name, what is that boot stage profile event, right? As I said, adding those two locks, again, we have to have a lot of discussion, understand where to add and what to add. So here it's basically start kernel. We just add after the setup arc, we add the timestamp of the starting kernel, and just before starting the user space process, we add the end log. I have also experimented to adding this head.s, which is the first one. We can add in the assembly code to have this counter read there, so it will give more precise to see how much time it taken from the U-boot to kernel handoff. Right, so you will get something like whatever you are saying here, the logs or boot tracker logs, you will see something like this here, where it is basically converting the counter value based on the frequency of what the ARM is running, right? It gives in the microsecond value, right? Then comes the third part of this is your record parser, where basically we read all those records, the messages, we parse it, we merge it, right? So what this utility does? First thing it does is map the boot stage reservoir, right? And then it will read the SPL and U-boot boot records. It will read all other components in your SOC, whatever is there, their boot records. It will read and pass the kernel boot messages. It does the time synchronization between MCU and DSP record with master time, and then merge into single timeline. And then finally, the output gets generated, which is basically your boot time report on the console, as well as it gives you the HTML, which you can view on your browser. So here, one more important thing, I think Francisco earlier has sent one RFC driver for the getting the timestamp from this boot stage area, right? So that is still there. So we didn't use that as of now because we don't know how many components will be there in your SOC. If it is only one MCU, or you have different DSPs, everything is there, right? So we are still thinking whether we should go with this mmap approach in the user space or go with the Linux driver approach. That's something we'll discuss more in our SIG meetings. Okay, so here is just example or simple demo on AM62X, where I'm just demonstrating when it boots up and how the report looks like. So it's just booting up your A-Course Linux, right? I'm sorry for the small fonts here. So it's booted up, and now I'll just run the boot parser utility, and you see how the logs report looks like. Maybe a little better over here, right? So if you see here, right, it gives you the overall the boot time summary, when the device powered on, how much SPL has taken time, how much U-boot has taken time, what is the kernel handoff time, basically from U-boot to kernel jump time, and how much kernel has taken time, and the total time. As I said, this is not with the user space integrated yet, right? That's something we have to do. Till the kernel start the first user space application, it gives the view. And then you can also view the different boot stages of the component. Let's say A-core or MCU, what exactly happened and what time, right? This gives you a view, like when the bootloader started, what happened at the U-boot R, DMR, Ethernet start, and when it started the MCU, you can see the MCU started at 2639 millisecond, and that is what you can see the MCU boot records. That's where we say MCU awake happened 2639. So you can clearly see, okay, from 2639, this is what happened at the MCU level, right? When your drivers are open, when your sync happen, and if you see there is a big gap, IPC sync for Linux. That's where the MCU was waiting for Linux to be up so that it can start the IPC process. So that's where it is waiting. So you can see all this timeline view here in this. Next, I will go to the graphical, how it is there. I will just do one, I'll show you the actual graph, this one, graphical view instead of, sorry, right. Okay, so very similar to that, in graphical view, you can also see what exactly is the boot summary, and then you can get this view, okay, what happened on your master core, right? Here, different stages and what happened at the MCU. And here you can also view each stage, boot stage, how much time it took it. So if you go to the absolute view, you can see here, right? Sorry, not absolute view, basically the duration view, you can see each stage, how much time they have spent there, right? Here it is currently in millisecond, but we have the microsecond, we can also have in the microsecond, but for the graph looks bigger, so that's the reason I moved to millisecond, but you can clearly see what happened, which component is taking more time at what stage. So you can clearly see this, right? And then, as I said, you can also see the view of absolute and delta for the different components in your system, right? So here you can see the bootloader and Linux layer, what happened, what exactly at each stage, what is the time they have taken, right? And similarly for the MCU, you can see what happened and what was the absolute time they have taken, and what was the delta over here in millisecond view. Right. Okay, so this is what I was displaying over here. So I thought in the slide, I will show you the actual one from the browser itself, right? Okay, so that was our proposal, whatever we are currently working, right? And there are a lot of improvement we need to do. We need your help, to solve those issues, mainly in the kernel perspective, what exactly we have to do over there, standardizing the boot time logs, markers over there. So that's where we need your help. So current status is that basically, as I said, it's single master boot, what is currently supported. We have to, basically the shared, whatever memory we are allocating here is static. We plan to do dynamic allocation if we are going ahead with the memory-based boot record logging method, right? As I said, it is only supported till your first user space application starts. So till that point, right now it is there. All whatever we have developed, the utility or the boot stage, MCU side, the framework which we talk, those are already available on the GitHub. So you feel free to go try it, see how it is there, and give us the feedback on that, right? The kernel and U-boot RFC patches, that's already there, sent to there. So those links are here. So please go ahead and try these things. See what limitations you are seeing, what issues you are seeing. Please provide feedback on that so that we can work on it and make it more, suitable, right? Okay, so that's where I think, Tim, this is where I want to invite everyone in this room to join us, the special interest group which Tim has created for boot time, so that we can work on more boot time ideas in projects which you are working, right? So this is one of the project which TI is working part of this initiative, whatever team has started, right? So I will welcome you all. Please come join us and give your feedbacks, insights, which we may have missed it because we may not see everything, right? But you have more experience on the different verticals you are working. So come give us those feedbacks so that we can improve more on this, right? And make this solution helpful for everyone. So we should not be worrying, okay, where is happening? Where is this boot time is increasing or decreasing? We should be able to see the complete holistic view of the system boot time. Right. So yes, there are some references from some of the previous UCs or talks from the other things, and also where you can find more on the boot time project ideas or activities which team is leading over there. So please come visit and see what we are doing on the part of boot sig team over there. So I sincerely appreciate and thanks Tim for starting this. I remember in the last plumbers, there was talk on this to having a special interest group or something where we can come together and work on all those things. So thanks Tim for creating this SIG, right? We appreciate really, and it is like it's very good journey, and we had a lot of good discussions happening, good project ideas are coming, so we welcome all you. Please join whenever you have time, help everyone here, right? Obviously TI is, I'm working there, so obviously I have to, I thankfully thank to them because they give me the opportunity here, right? Okay, so I think that's all from my side. As I said, this proposal, whatever we are talking, it's not the final solution or anything. It is just the initial approach to solve the problem which we discuss. So feel free to give your feedback so that we can improve this, right? Now I'll open for the questions. Thank you. Yes.
So are you statically compiling in the clock frequency for the different clocks that you're getting timestamps for? You're saving the clock values in microseconds, right?
Right.
So is the like the EL0 frequency, is that statically compiled into U-boot or in the kernel, or?
No, it is not statically compiled. It is read from the under ARM register. I think there is one more register which we are reading the frequency, what frequency that is running. It is not statically compiled. Yeah.
Just a comment, this value is often overridden from the device tree because it's not written correctly by boot firmware, so you might want to still read it out somewhere.
Right. I agree. I completely agree on this. Sometimes it happens. That's where we are trying to refine more of this one. As I said, this proposal, we want to show how we can do it, right? There are underneath framework, which still we have to refine. Basically more on the time sources, what we are talking, right?
I would like to share two adjacent mechanisms that we are already having.
Mm-hmm.
One is in U-boot, you have these trace events.
Right.
That are in F-trace format. Mm-hmm. And another thing, you have keystore or RAM oops as a backend. Verbox is using it to concatenate its own log.
Okay.
Log of the kernel. So in the kernel, if you do T-message, you see both behind each other. And I would believe that if you combine these two together, it would be better than any NEO format.
Yeah, good suggestion. I really appreciate that. I think that is a good way we can do that as well, right, Tim? I mean, we have to see if it works well for other architectures as well. Yeah, we'll try that. Thanks for the suggestion. Yeah.
Coreboot also has timestamps and logs that are stored like in coreboot memory, which is passed also to the kernel. So it's like a reserved memory block which has like different sections.
Yeah, right. Means I have looked through that, right? And we are, as I said, right, we are still trying to figure out whether we should go with the reserve memory approach or not. Okay. Really, we don't want to go with the reserve memory. We're trying to find some other ways to do this one. Yeah. Please go ahead.
Yeah, so you also, focusing on the boot time approach, you essentially developed kind of trace profiling for boot time, but kind of echoing what was already said on the F-trace. This is a general thing about tracing and profiling, right? If you focused on the boot stage from U-boot, the other commonality here would be F-trace from the kernel. There's lots of other places where the kernel is interacting with other cores, right? Not just at the boot time. There's power management activities, there's remote proc stuff happening.
Right.
The system that's nothing to do with boot time.
Right.
You want to trace and profile and unify some of that stuff. So my proposal would be that the unifying piece here could actually be F-trace. Because a lot of bootloaders are already using F-trace, it already has the notion of shared buffers.
Mm-hmm.
And so if F-trace was the commonality, we could also be using existing F-trace based tools, Kernel Shark and Perfetto, and a lot of other visualization tools that exist, and you already mentioned a few, chart or whatever.
Right, right.
And so that's, I would argue that's, ftrace is more common than U-boot's boot stage thing. And then it's not, you could use it for boot time, but you can use it for all these other interactions between other cores.
I agree, but here the one thing I differ is, yes, you boot kernel, it's all good, right? I agree with this, right? But when it comes to the other cores, right, where there's no Linux or some bare metal code is running, some RTOS is running, right? So that's where we want to have a very light framework so that it can go there and it's in for everywhere, not only here. I agree, means over the time maybe we can go ahead, no, the Linux side we can have this ftrace more, what is it?
You don't need ftrace itself, you just need the trace buffer format, which is just like a boot stage format in U-boot. It's just a memory structure that's got existing definitions, and it's very flexible already. So that you don't need Linux on these other cores, just like you don't need them.
Correct.
Users are just writing U-boot boot stage records. Instead of that, they should write ftrace buffers.
Right.
Still the same idea, but the other problems you identified are the same. It's how do you share the memory? How do you pass the memory?
Right.
How do you synchronize timers? Those problems still exist.
Right.
I'm just arguing that the common thing, rather than U-boot boot stage, the common thing could be ftrace buffers.
Yeah, we can look on that as well to see. I mean, maybe we can discuss more on this to see if we can. Oh, go ahead on this one. Yeah. Next. Yeah. Hey.
With the parsing, sorry,
Yeah, go ahead.
with parsing init called debug, we're able to use bootgraph.pl
Correct.
to get the detailed flow of what's taking time within the kernel boot. If that can be unified in here,
Yes, that's if you see here, integration with boot chart, system and live. This is also part of our future plans, right? Okay. So that we'll be working on by future.
and second thing is, within MCUs and DSPs, you'd have to annotate the code, right?
You have to add a small piece of code.
Who has access to that code? Is it open?
It's open, as I said, right? If you see here, right? The MC boot stage logging, so you can go ahead. It's already there. You can use it on your specific MC or DSP.
It's on whichever platform we're doing it. This also needs to be available, right?
It's available. It's not platform dependent. It's platform agnostic. You can use whatever platform you have. It's not related to only one MC or one DSP. No, it's plain.
Not the code, but the source code where you have to add these.
That is you know your code better, right? Your core, what you want to profile in your, right? So,
Would have to contribute to their own.
right. We given the reference how it is there on whatever we have done, right? And then you can take a reference, what points, how to add it. That's something to see. Okay. I think we are out of time. Maybe we can take some of the discussion later today or over our SIG meetings, right? And I thank you everyone for taking your time and attending this session. Appreciate all. Thank you.